this morning. It was a lot of fun. So today I'm here to talk about how we can use consumer health devices to improve healthcare. So as we know, there's a lot of devices that we have today: wearables, smartphones, social media, websites, consumer-grade medical devices like blood pressure monitors and continuous glucose monitors that are in widespread use today, and which can allow us to create things like digital diagnostics, adaptive digital therapies, and other such healthcare applications that would not be scalable and accessible. So I'm going to talk about some of the work we do and talk about cloud computing specifically with respect to AI and privacy, because we work with a lot of health data, with crowd computing, which is a subset of cloud computing, but using platforms like Amazon Mechanical Turk, as well as federated learning, which is an approach to handling when do we train on device versus on the cloud, and what's the process for communicating back and forth. So I'm going to guide this talk by two fundamental challenges and corresponding opportunities in the field of consumer digital health. So the first major challenge when working with data coming from these sorts of devices is that the outcomes we like to be able to predict with these devices are often highly subjective, heterogeneous, and differ a lot across individuals. So it's subjective, especially in psychiatry and behavioral sciences, which is a lot of what I work in. So for this, what I propose is human-in-the-loop AI, which is probably a lot of you already know, but where we have, instead of just building a deep learning model, deploying it and calling it a day, we have a human work together with an AI model in order to achieve a synergistic outcome that would not be feasible to achieve using just an AI model, and which would be unscalable using humans alone. So that's one half of this talk. The other half has to do with the data themselves. The challenge here is that the data are incredibly noisy and drastically vary across subjects in terms of the patterns of how they wear their device and all these things that introduce a lot of noise. So for this, I'll talk about personalized AI, where instead of the status quo of building a one-size-fits-all AI model, which is often used in AI for healthcare, like we build this one model, we're going to give it to everyone, it's going to diagnose. Instead, we build a separate AI model per person, and for diagnosis, it doesn't quite make sense, but for applications where we're predicting a repeat adverse health event like a blood pressure spike or a blood glucose fluctuation or stress or things like this that occur repeatedly for an individual, we can essentially overfit the model to that person, but it's fine because it's only going to be used on that person. And I'll talk about how we can use self-supervised learning and essentially the technology used to train ChatGPT, but using wearable biosignals to make this possible. And people keep making fun of me for doing this when I've given this talk, so I'll stop. So I'll start with the first half, which is human-in-the-loop AI, which is work that I've working on in collaboration actually with a PI at Stanford, Dr. Dennis Wall, who I did my PhD under, and now we're writing grants together and collaborating. So what I'm going to talk about is in the field of autism, which is a condition that affects 1 in 40 children in the United States. And it's characterized by a wide range of behavioral characteristics, such as lack of eye contact, trouble with social responsiveness, and several other behavioral characteristics. Now, when you hear people talk about autism, you probably hear it referred to as a spectrum, like this one-dimensional spectrum, and anyone falls somewhere on this 1D scale. But actually, more recently, researchers conceptualize autism as several independent spectrums, which makes it very complicated to study because, for example, you could have a child with high emotional sensitivity and low motor skills who is said to have autism. You could have a child with also high emotional sensitivity, low motor skills who doesn't have autism, and you could flip it, and you could get autism or no autism. And I'll talk in a bit about why that happens based on the diagnostic process for autism that clinicians go through. But because it's so complex, it results in extensive waiting times to receive a diagnosis, which results in delays in receiving care by clinicians. In the United States, that average waiting time exceeds 18 months on average, which is a problem because it's been repeatedly documented that the longer you wait for a diagnosis, the longer you wait to receive care, and that often leads to reduced and worsened life outcomes for children. Not always, but in some cases. And unfortunately, this problem in delayed care has resulted in systemic discrimination of underserved and marginalized populations who really don't have access to care and are not going to be able to receive a diagnosis perhaps ever. You know, the parent is working, doesn't have time to drive, or all these other issues that prevent the diagnosis. So I firmly believe that digital devices can help. They're ubiquitous. Almost everyone has a smartphone today, at least in the United States. And so if we can use these devices that people have anyways to do something like a screening in a remote, scalable, and accessible manner for mental health and autism and in a wide range of other conditions, then we could perhaps bring care to those who have traditionally been left out of the healthcare process. So before I go into the AI side of things, let me tell you a bit about how a clinician diagnoses a child for autism. And really, this is not specific to autism. This is anything in psychiatry and behavioral sciences. So when a clinician is evaluating a child for, let's say, autism, in this case, they evaluate the child with respect to several behavioral characteristics and rates the child on a categorical ordinal scale. That's a fancy way of saying the 0, 1, 2, 3 Likert scale, from 0 to 3. And 0 may correspond to never exhibiting the behavior, and 3 corresponds to always exhibiting the behavior. So let's say a clinician's evaluating a child and rates the child as a 2 for facial emotion expression during conversation. So that might correspond to often emotes during conversation, not always, not never. So the clinician will record that on their score sheet. The clinician then proceeds to do this for a bunch of other behaviors, and when this process is done, this is how the diagnosis is derived, they sum up these numbers. And if that sum exceeds a threshold, the child receives the diagnosis. If that sum does not exceed the threshold, no diagnosis is provided. So I hope it's clear from this how there are many paths to exceeding that threshold, right? And that's why you get so much diversity in what is called autism. It's exactly because of this process. So from a machine learning perspective, that makes it really hard to then try to automate this, but this is what we're working with. And so what we did actually back at Stanford was to train a machine learning model to predict the diagnosis of autism given data sets that already exist of these clinician-filled score sheets in order to understand which of these many behaviors are most predictive of autism and which are not so predictive or which are not necessarily required if we want to do these automated approaches. And so we did something called feature selection, which is a machine learning way of determining which inputs to an AI model are most predictive of the output. So doing that, we can remove those features that are not related to autism. So eating frequency isn't on there, but if it was, it would certainly be removed, and prioritize those behavioral features that are highly predictive of autism. So the next step is, okay, now that we have these features, we can use them to predict autism in an automated way using computer vision and all this. The problem, as you might know, is that even though ChatGPT and AI and generative AI is doing all these amazing things, human social behavior is really complex. And I have an experiment right now asking ChatGPT to annotate these behavioral social features based on text transcripts. It does a horrible job. We're working on a paper just showing that, because all the papers now are like, look what ChatGPT can do. But I think this is a powerful negative result of We'll look what ChatGPT can't do. And so this is an example. So if you, for example, give one of these generative AI solutions, for example, a video of a child who may or may not have autism, and ask it to tell you, does this child enjoy participating in social games and interactions? Can't do it. And this is one of the top-rated features, and here's another example. But the thing is, humans are good at this. Not all humans, but many humans can watch these videos and do a pretty good job, and they don't have to be expert clinicians in all cases. So what we looked at doing back at Stanford, but now we're expanding upon this in our collaboration, is to use Amazon Mechanical Turk, a crowdsourcing platform, to see if we can get crowd workers to watch these videos, do the annotations, and then feed those annotations into a machine learning model to do the diagnosis. Of course, this is with publicly available videos. I'll talk about when they're private PHI videos, what we can do when we can't use MTurk. But for now, let's assume these are public videos with consent to share them publicly. And what we can, so for those who don't know, by the way, who's familiar with Amazon Mechanical Turk? Okay, this group knows it, so I don't have to introduce what Amazon Mechanical Turk is. So what we did was we posted a hit on MTurk where we put these public videos up there. We know the diagnosis, and we asked the crowd workers to answer a series of multiple choice questions about what they observe in the video, knowing nothing about autism, just answering about the behaviors they see in the video. As the crowd workers answer these questions, it results in the corresponding categorical ordinal behavioral feature vector populating what I like to call a behavioral feature vector, and then we could feed this into an AI model that will predict the diagnosis of autism. Well, where do we get this gold standard model that these behavioral features are entered into? Well, I just already told you about that. We have the feature selection process from these clinician score sheets that we can use, so we could essentially take the output of the crowd workers, get a much more usable feature vector space, feed that into the AI model to do the final diagnosis. And so I actually have a lot of slides here, so I'm going to skip all this. And long story short, does kind of well. And so great, does great, we're done, right? Well, not so much. The first thing you might ask is, well, maybe the videos we were using in the test set are super easy to diagnose. In other words, the videos of children with autism are clearly depicting autism, and those that are neurotypical children are clearly neurotypical. And so to get a handle on this, we had clinicians watch these videos and annotate the severity of the child with of the autism based on something called a clinical global impression rating. And basically what we found is that the autism that appeared in our data set was skewed towards the severe according to this CGI rating language. And so that means that this was an easy data set. So yeah, we get really good performance, but that's not too impressive, right? Because it was an easy data set to classify. So anyways, there's a lot of subtleties like this on these slides, but I'll skip all that. I'll mention we looked a lot into privacy. How does this process work when we're applying privacy-preserving modifications to the videos in the data set, and we find that it degrades and blah, blah, blah. We look at all that. So, okay. So let me talk a little bit about cloud computing implications of this work. So starting with this middle bullet point, if we're going to incorporate these humans in the loop for this process that does work pretty well, it has to be for non-PHI, right? We can't put PHI up on MTurk. So, okay, this is good if somehow you get these videos to count as non-PHI, so that means they're voluntarily shared and it's totally transparent with the participants that they know this is what's gonna happen with their video. If that's not the case, we have to create a PHI-compliant environment. And so that's actually something we did as well, where we used Amazon Web Services, because that's where we had a lot of credits from, and we built a secure platform that's HIPAA-compliant, which allowed workers that we recruited. We had the workers then go through city training to encrypt their laptops, go through, actually become members of the research team. So what we ended up using MTurk for was determining, okay, who's good at doing this? And then let's recruit them. Actually, funny story, I got banned from Amazon Mechanical Turk for doing this because you're technically not supposed to recruit people off. So then I moved to this other platform called called microworkers.com, which doesn't impose that restriction, and so we got people there. It was kind of funny that I got, just doing my PhD work and got banned from MTurk. But anyways, it's all good now. We worked it out. We don't do this anymore. Okay, so HIPAA-compliant options. So turns out the three major cloud computing providers are HIPAA-compliant. So AWS, of course, but Google Cloud and Microsoft Azure have ways to easily make your solution HIPAA-compliant. It's just because it's on these platforms doesn't mean it's HIPAA-compliant by default, but it's basically you check a few things, and it's much easier than building a HIPAA-compliant system from scratch, which is a lot of work. So what we built is essentially a standard workflow for annotation from crowd workers that we recruited, using S3 for storage, EC2 and EBS for web hosting, and DynamoDB for storing metadata. I did find a checklist of best practices for ensuring HIPAA compliance on AWS. And as you can see, it is a long checklist, but a lot of these things are not too hard to do, like enable backup for RDS instances. Okay, you check the box to do that. Don't make S3 buckets open to the public. Check that box. So it's some things you have to do, but it's not excessive. And I've been involved in doing not all of these, but a lot of these. IAM roles, you'd probably want to do that anyways. Encryption, things like this. Some of these are a little bit more work, like the data backup and audit logging. But again, with CloudWatch, or I forget what it's exactly called, but there are solutions on AWS to do all this. So I assume I haven't tried to build a HIPAA compliant solution on Google Cloud or Azure, but from what I can tell, just going on their websites, there are similar solutions for making it HIPAA compliant. So anyways, that's what we did. So in summary, in this first half of the talk, I talked about a solution and kind of rushed through it, but how do we have humans and AI work together? And how can we make sure that the humans that are involved in this process are doing so on a HIPAA compliant web service, and that they've gone through proper training protocols to ensure the privacy of the human subjects that are involved. So happy to talk about that, but now I want to shift gears to the second half of my talk today, which is on the personalized AI side, and specifically for personalized deep learning using wearable biosignals. I said I wouldn't do it, but can't help myself. Wearable biosignals. And so specifically, the framework that we're working under is to train a separate AI model per person. And so the type of data that I'm interested in is multimodal time series data that come from a wearable device, for example, a Fitbit, but it can be anything, where we have several biosignals that are recorded over time for each participant. So for example, heart rate over time, SpO2 over time, et cetera, et cetera. Those would be the inputs to the AI model. And then we have annotations of some sort of adverse health event that occurs repeatedly for that person. Blood pressure spike due to stress, glucose fluctuation, things like this that we want to be able to monitor and detect in real time and then intervene accordingly. And so what I like about this approach is that because we're essentially overfitting the model to each person, but in a good way, we're enabling prediction of outcomes that would traditionally be way too out of scope for machine learning. Like stress, for example, that's such a subjective thing that varies across people. But internally, within one person, the triggers of stress can be consistent. not for everyone, but you could assume that for many people, it would be consistent. And so if we can have an AI model that can learn how does their heart rate change when their skin temperature changes and when they get more stressed as self-reported by them, it may be possible. And so some of the projects that we're starting to explore and getting some reasonable preliminary results is predicting substance craving and use in real time using biosignals. And again, the way I like to set up the projects is so there's a low-hanging fruit and then a high risk, high reward. So substance use would be kind of pretty easy, right? Because like if your heart rate's spiking by 3x and you're not moving, probably you're not exercise. Anyway, so like it's, use is doable, and there's prior literature showing that that's possible. But substance craving, that starts to get into that subjectivity world. Kind of, if we can make it work, that would be high risk, high reward, right? Because now we can predict something and intervene before it happens. There's only so much you could do to intervene once someone is already using. But anyway, so this is something that we're working on now and starting to get some promising results. And another one we're working on is detecting stress and stress-induced blood pressure spikes, where the blood pressure spikes are actually measured by another wearable, really cool. So Omron, a blood pressure monitor, actually has a wearable watch. I didn't bring mine here, but it just cuffs and records your blood pressure. And so then we could predict, okay, how can these really non-invasive watches be used to predict blood pressure spikes caused specifically by stress? So the key to making this work is self-supervised learning. So I know everyone knows about MTurk and about cloud. Who here is familiar with the idea of self-supervised learning? Okay, so let me teach you for a couple minutes. So turns out that self-supervised learning is the key to training ChatGPT. Who knows about ChatGPT? Okay, so let's start from there. So the way that OpenAI trained ChatGPT is to download all the text on the internet that they can get their hands on, and they trained the machine learning model kind of in a conceptually simple manner. The model itself wasn't simple, but the way they trained it is, it's given a few sentences, predict the next word in the sentence, and do that for a bunch of text. And so why is this good? Well, two fundamental reasons. First is that so much of AI training is bottlenecked by having good labels. But for this, you don't need human labels. The labels are inherent in the data, right? You take any 9 words, that's the input to the model. 10th word, that's the output. You don't need any human involved there. So now your only bottleneck, OpenAI's only bottleneck, was how much text could they get their hand on. And they scraped Wikipedia and public websites, and Bard said they didn't use Gmail, but who knows? And so just whatever text you can get your hands on, that's the training the model. So that's the first benefit. The second benefit is, okay, once you do this, if you have a model that can predict what's the next word given the previous sequences of words, then you have a model that understands human language pretty well. And then fine-tuning that model to a task like responding to a prompt well doesn't require crazy amounts of labeled data anymore, because your starting place is a model that already understands human language. And so that was kind of the key innovation of ChatGPT. So now you know how ChatGPT was trained, or at least half of it. This is the first step out of 2. So what I'd like to do is apply the same principle, same method, to wearable biosignals, where instead of predicting what's the next word, given the previous sequences of words, we predict what's the next biosignal reading, given the previous biosignal readings. And now we could take advantage of people just wearing their smartwatches and doing nothing, just going about their day. And now suddenly we have a massive amount of data per person and a massive amount of labels for the self-supervised pre-training, for which we can train a baseline model that understands the temporal dynamics of their biosignals. How does their heart rate change when they move? What is the relationship between their skin temperature and electrodermal activity for that person? And so when we have these personalized foundation models, and the starting place is a model that understands their variation in biosignals, doesn't take too many additional labels to fine-tune to these really challenging tasks like predicting substance use and craving or blood pressure spikes. And so we can make the models a bit more complex and extend what I just described by predicting what's the missing portion of another biosignal given two or more different biosignals. And yeah, but that's the basic idea. And we found that it works pretty well. I don't want to bore you with the results, but basically what we found is that on a bunch of publicly available data sets, it works quite well. And maybe I'll just link you to the papers for these. Long story short, it performs quite well on a bunch of data, but data sets that were collected in the lab. Now, what happens when we get data that are outside of the, in the wild, which is what we really want here? Well, so in contrast to these pretty easy data sets we first looked at that were collected in the lab in highly controlled settings, we next wanted to study, okay, what about the opposite end of the spectrum, incredibly challenging data sets? So what we found is possibly the hardest data set you could imagine. This is a data set of nurses who were working during the beginning of the COVID-19 pandemic and asked to self-annotate their stress while they're working in the beginning of the COVID-19 pandemic while wearing their wearables correctly and while annotating correctly and consistently. So as you could imagine, this didn't go over so well, and specifically there was inconsistent labeling across nurses, which you would think personalization would be able to account for, but there was also inconsistent labeling within the same nurse. And there's not too much personalization can do for you there if there's not consistency within an individual, and that's because they're stressed and asked to do a lot, and already, COVID was a lot of work back in 2020 when this was collected, and so asking them to do all this annotation of their stress on top of that, as you can imagine, was quite challenging. So this highlights the need to go beyond these simple data science approaches and incorporate human-computer interaction innovations into the mix. And so my lab is now looking at several ways that we could combine AI with HCI, human-centered AI, to make this possible. So one idea that we're exploring right now is to look at the output of the AI model trained so far, and if that output is so these AI models output a probability score, which is a confidence, right? So if it's a high probability or very low probability, it's highly confident. No need to ask the user for a label at that time. But if it outputs 56%, which is basically in the middle, it's not too confident, that would be a good time to ask the user for an annotation. So solutions like this, where we could essentially use the AI model, continuously train it over time to ask the user for an annotation at the right moment. And the other benefit of this is a lot of times the nurses weren't wearing the wearables correctly. And so in those cases, the model's not even going to output something. And so we don't even bother asking them for anything if the model's not working so far. So it could also help with user compliance. On top of this is not a great picture demonstrating it, but we're looking at user interface designs that are specific to the health conditions that we're studying and incorporating participatory community-based design principles to come up with ways to design for our communities in a way that will enable good data collection at the same time. And so, this is highly dependent on the community we work with. So like one project we have is Parkinson's, and a geriatric Parkinson's population is going to be very different than a pediatric autism ADHD population, and kids and adults and different conditions. So we're designing separately for each population that we study, bringing them into the lab, interviewing, co-designing so that we're not just developing things for them, but with the community. Okay, so cloud computing implications on this side of the research. Well, there's a lot of opportunity for federated learning approaches. So who's familiar with federated learning? Okay, so this audience might find this interesting. So federated learning, let me see if there's a slide on this. Okay, is basically a solution that at least Google Cloud and Azure have a solution for. I think AWS has has it too, but I've been giving lots of love to AWS. So to give some love to Google Cloud and Azure, they have some really nice federated learning libraries. And basically the way it works is that if you're training a separate model on different people's device, you can train the model locally on device, and then you could upload the trained model, not the data, but the model up to the cloud. You can then aggregate all the weights of those models to create a really good global model, and then you could send that back to the individual devices so that everyone gets a better model. So why is this useful? Well, few reasons. One is privacy, right? A lot of people worry about sending their data over to the cloud and privacy reasons, but using this approach, the data don't need to leave the user's device. All the training happens on the device, and then all you're sending is like all these numbers and coefficients of models to the cloud, but there's no sensitive data in those. And then you aggregate it together, send it back to the device, then everyone gets a better model. It's essentially as if you had trained using everyone's data. All the users get the benefit of that type of model, and yet they get the privacy benefits. Another benefit is that it can help with low network situations, which is a lot of what I care about doing digital health in populations and with individuals and families who don't typically have access to internet consistently. And so this could be good for this as well, where we can train a low-cost model on their device and then only upload it whenever they happen to connect to Wi-Fi, whenever it's available. So it's a little bit of a delayed access to the model, but it is still, they still end up getting in a few days or whenever they access the internet next, a model that anyone with high connectivity would get. And there's several other benefits too. It's a distributed way of computation. For people like me as a PI, it can reduce cloud computing costs, right? Because we're just aggregating models on the cloud now, we're not training. So anyway, there's a ton of benefits to this. I'm happy to talk more about federated learning. And so I thought this diagram would be a little helpful. So there's two types of training steps to what I described today. There's pre-training, and then there's fine-tuning. So the pre-training is that self-supervised learning. I talked about the predicting the next word given previous words. That's in AI, we call that pre-training. And then fine-tuning is taking that pre-trained model and optimizing it for the task you actually care about. So responding to prompts or predicting substance use. And so for pre-training, so cloud works great for pre-training and fine-tuning. For pre-training, though, it's not really feasible to do on-device pre-training with federated learning because it is expensive. It requires, you're creating a lot of data points synthetically. So it does require a lot of compute. But for the fine-tuning, you can totally do that on-device. So this gets into just interesting discussions of when do we offload our computation to the cloud, when do we do it on device, and that's something that as a digital health lab using consumer devices, but training large AI models, I think about a lot. So yeah, that's all I wanted to talk about. I skipped through a lot of things, but happy to talk a lot more in Q&A. But to summarize, I talked to you today about two big thrusts of our research lab. One is in human-in-the-loop AI, where we have humans working together with AI models to enable diagnoses in psychiatry and behavioral sciences. And the other is personalized deep learning to enable prediction of recurring adverse health events. And I talked to you about AI and privacy, crowd computing, and federated learning. So with that, I'd like to thank all of my mentors, research collaborators, clinical experts without whom this wouldn't be possible. Of course, NIH, who's here. Of course, AWS, who's here. Thanks for the credits. And my many other funding sources. So thanks so much for your attention.
All right, questions? Cornelia, if you can get Tim there.
Great presentation. Tim from Internet 2. Curious, with using machine learning, how do you see machine learning helping with personalized support for kids with autism? For example, using indicators or metrics to see, okay, we should maybe put the child to some sort of sports program or educating them with additional math classes because they happen to be great at math. So things like that. How do you see machine learning being applicable to improving their growth?
Yeah, that's a great question. So actually one project that we worked on while I was a grad student at Stanford in collaboration with, well, Dennis Wall led this, but was to build a therapeutic on Google Glass back when people thought Google Glass was, gonna take off. But basically, for a lot of children with autism struggle with recognizing facial expressions during conversation. And so this was meant to be as an educational aid for children to basically wear the Google Glass during conversation, during sessions, and to get, basically the way it worked was the AI was detecting the emotion of their conversation partner and displaying that feedback in real time on the Google Glass. And then eventually, one nice story we found is that some of the children participating in the study, the parents told us that the teacher of the student, of course, was told the parent, wow, the child is looking at my face now and being much more emotive. And the teacher knew nothing about this study. But just hearing stories like that, brought a lot of meaning to what we do. And so, sorry, the personalized part of this is that we fine-tune those emotion recognition models to optimize them to recognize the emotions of their parents' facial expressions, because everyone expresses emotions differently, and that's a big challenge of generalized emotion recognition models, and that's why their performance is always like in the 70s and 80s in the literature. But when you personalize it to each person in the child's family, then you could get much more performant emotion recognition models.
Thank you.
Oh. Yes.
Oh, hi, my name is Sashi Pillai, University of Nevada, Reno. So I'm interested in your statement about how do you go about selecting the appropriate features that has the maximum objective value. Mm-hmm. So can you talk a little bit about what you did in terms of algorithms or techniques you used to do that?
Yeah, so basically it's a relatively simple approach. So these feature selection models give you a ranked list of what are the most predictive features, and we looked at a variety of different feature selection approaches. Some look at each feature individually, some look at each feature in combination of other features, like a decision tree does that, for example. And so what we did was essentially make a plot where the x-axis is the number of top-ranked features, y-axis is model performance, and you essentially get a curve, which is a really interesting curve because it kind of goes up like this, but then eventually it starts going down. And so we try to find the place where it's still good. Because the reason it starts going down is when you have too many inputs to the AI model, you start to overfit. It starts to learn these things that aren't really useful for prediction. And so you want to find that sweet spot where it's, but also we can go a little bit down before it hits the inflection point so that it's not too much work for the people creating the features for the AI model. So it's both this quantitative consideration, but also practical considerations that jointly go into the decision.
So the objective function is basically based on a trial and error process as opposed to
Yeah.
value, right?
Yeah, so the comment was that, is this based on a trial and error process? I guess so. I mean, try each feature, get the performance. A lot of AI is done that way, like hyperparameter tuning. So just another example of that.
I'm Jim Charters at the University of Michigan. I'm curious, sort of anecdotally, what are your observations around the quality of the measurements of some of these wearable devices? Like, I'm sure there must be a variation of like good devices, bad devices, readings that are accurate versus readings that tend to not be accurate. Just curious what your observations have been.
Yes, great question. Yeah, there's a lot of variability in it. So for Fitbit, for example, there's a lot of, so for example, we can get step count and heart rate at a minute level granularity continuously while they're wearing the devices. Now, some of these other measurements that they say they provide on their website, like SpO2, heart rate variability, you only get them during sleep, but it's not upfront on the website that's a limitation. And so, for us, we have to get really creative with how we train these AI models, because it's like, okay, we have some signals that we get at a per minute granularity, and other signals that we only get during certain parts of the day. So when we build these multimodal deep learning networks, we can't just use out-of-the-box model. We have to create really specific architectures to handle those differences. And then there's other, like different signals have different sampling frequencies, and we have to handle that and all this late stage, early stage fusion. So it gets really interesting from a neural network architecture construction perspective. So there's other devices too that are much better. So one of these that I'm wearing, Empatica, is really good. It records everything. You get the raw biosignal. So you don't get like Apple Watch or Fitbit that pre-processes it and gives you the output of that. You get the raw signal, and there's a lot that we can do there. The only real issue with Empatica I found is the cost. So, you could spend $150 on a wearable or $2,000 on a wearable, and you get what you pay for, is essentially what I'm learning. So in terms of like writing NIH grants, like feasibility study, 1 or 2 of these, and maybe a lot of these, and then once the R01 comes in, get a lot of the expensive ones.
Hey, Sarkis Daglian, UC Irvine. Question, so in future, so let's say I have a personalized AI, it looks at the pattern, let's say my blood pressure's about to spike, increases like the possibility of an adverse incident, like a heart attack. Like what is the future design for like the feedback loop on that? So like the AI knows this pattern is happening, like is there any sort of roadmap for having like a feedback loop back to the individual, like hey, the device is noticing based on your prior patterns that you're now at higher risk for an adverse health event?
Yeah, that is the end goal, is to create that feedback loop. What exactly that feedback loop will consist of is TBD, and that's, this community-based participatory design will inform that. I don't want to say, oh, I'm going to develop this exact solution, because I want to bring the participants in and to help me inform of what would be useful, as well as clinicians. And I do have some active collaborations with behavioral scientists who can also tell us, okay, from their perspective, what are ways that they know that would induce behavior change based on prior literature. So a lot of this is team science. I'm not making all the decisions here. But that's a great question and something we are actively thinking about.
All right, last question up here.
Hey, we have a question from one of our online participants. Do you plan to work with clinical trial teams to see if your model can predict which medication can work better on kids diagnosed with ADHD, ADD, or anxiety and depression?
That's interesting. No, I haven't considered working in the medicine side of it. Or I'm focused more on the behavioral intervention side, but I do think that is interesting. I mean, there's a lot of medications that are prescribed, and I don't need to go into that. But in short, I'm not too interested in helping in that way. I do think there's a lot of aid that can happen simply through real-time behavioral intervention.
All right, Peter, I want you to show your wrists.
One last time.
Do you know what time it is? I mean, how could you tell? All right, join me in thanking Peter for that great talk.